So we're adding on to our area formulas in 10.3 with the area of regular polygons. And this section is all about just using one formula to find the area of our polygon. The catch is that it's going to take a little bit more work to get the pieces for that formula sometimes. So we're going to skip ahead from that first activity. You might look at that together in class. We're going to go straight to the definitions of our pieces of that regular polygon. So the area of a regular polygon is related to the distance from the center to a side. We can circumscribe a circle about any polygon. That means to draw a circle around that polygon. The center of the regular polygon should be the same as the center of the circumscribed circle. So if I refer to the radius of the regular polygon, that's the distance from the center to a vertex. So going from the middle out to a vertex of the polygon, meaning to one of those angles. So a radius would be any of those dotted lines. The apothem is the perpendicular distance from the center to a side. So this would be side in there, but not vertex. So want to make sure you have that correction in there. If I go from the center to a side, again, that's drawn in there as the apothem. So not to a vertex, but from the center to the side is what we're going to describe as the apothem. The central angle of a regular polygon can be found by taking 360 for the circle and dividing that by the number of sides that you have. So for example, the measure of the central angle below, if I take 360 and cut it into, it looks like 1, 2, 3, 4, 5, 6 pieces for 6 sides, 360 divided into 6 would be 60 degrees for each central angle. So it's a little hard to see there, but I have the little arc there for my central angle, and since I have 6 of them, they should all add up to 360 if I put those all together. So we should be able to find those angles if they're labeled in my figure. And in this case, if I have a regular pentagon, if I have 3 angles that I'm looking for, so angle 1 looks like it's going to be a central angle, then I'm looking for also angles 2 and 3. I can find the measure of angle 1 just by using my rule from the last page. If I take 360 for the circle and cut it into 5 sides, 360 divided by 5 should make each central angle 72 degrees. So angle 1 would be an example of a central angle. Angle 2 is just taking a central angle and cutting that in half. So if I take my previous answer for 72 and I divide that into 2 pieces, I get that angle 2 would be 36 degrees. And also to answer for angle 3, if I notice that we've made a right triangle without apothem, then if I take 180 and subtract out the 90 and 36 for those other 2 angles in the triangle, I'll end up with a remainder which is 54 degrees for angle 3. If I know it's a right triangle, you could also just do 90 minus angle 2, and that will get you a little bit faster way of getting angle 3. Same type of question for the next one, but this time if I have an octagon, that's going to tell me how to find my central angle. So angle 1 is another central angle. If I take 360 degrees and divide that into 8 sides for an octagon, that means I would have 45 degrees for a central angle for angle 1. And angle 2, just like last time, I'm going to take that central angle and cut it in half. So 45 divided by 2 should give you 22.5. And for angle 3, again, I can do 90 minus angle 2, or 180 minus both of those. 180 minus the other 2 angles in the triangle, I'll end up with 67.5 degrees left for angle 3. So if 2 figures are congruent, we also know their areas are equal, and that's going to be helpful with some of these area formulas we're going to deal with. Suppose we have a regular n-gon with side S. The radii divide the figure into n congruent isosceles triangles. So kind of like how those figures were portioned up before with those dotted lines, we can split our regular polygon up into a bunch of triangles. The areas of these isosceles triangles are all equal because they should all be congruent figures. Each triangle has a height of h and a base length of s. So the area, has a height of not h, it has a height of a, because that's my apothem, and a base length of s. So the area of each triangle, 1/2 base times height, is 1/2 s times a, or a times s. Since there are n congruent triangles, the area of the n-gon is n times that triangle area we found from before, 1/2 a times s. And the perimeter of the n-gon is the number of sides n times the length of a side s, or again, just ns. And if we do substitution, so if I take that ns and I replace that with the perimeter, I end up with the area is going to be 1/2 apothem times perimeter. And after all that, that's the only part we really care about, this very last equation, because that equation is going to be using what we're finding for our areas of any regular polygon. So again, that formula is going to be area equals 1/2 apothem times perimeter. If you're not really sure about all the stuff that came before it, that's just kind of an explanation as to how we got that formula. But again, in terms of our work, the only equation we'll actually need is this last part. So as long as we know where these pieces are coming from, if I take the apothem and if I know the perimeter of my figure, I can substitute those in this equation and end up with my area for any of those regular polygons. So trying that on the back, we know that we're trying to look for the area of this regular decagon. And if I use my formula, 1/2 apothem times perimeter, here they're just telling us the apothem is 12.3, so I know that to start with. I also know for my perimeter, if my side length is 8, my perimeter is going to be 8 times 10 because I have 10 sides. So 8 times 10 should give me 80. And now that I know the apothem and the perimeter, all I have left to do is to substitute. So 1/2 apothem times perimeter is 1/2 12.3 times 80. And if I enter all of those, I should end up 492, and that would be square inches. So next one, I'm not given a figure, but we're told it's a pentagon. And I also am told the apothem and the side length. So I should have enough to substitute in my formula. If I'm using that same formula for area, 1/2 apothem times perimeter, all I'm going to do is use the 8 that they told me. And if each side is 11.6, and I know I'm dealing with a pentagon, I'm going to do 11.6 times 5 for 5 sides, and that should tell me my entire perimeter is going to be 58. So substituting those two that we found, 1/2 apothem times perimeter, should end up with 232 square centimeters for that second one. So next one's a little bit of a conceptual question. If the side of a regular polygon is reduced to half its length, how does the perimeter of the polygon change? And for this, you can kind of just think back to how we find the perimeter. We get the number of sides times the side length, kind of like what we did here. We have 5 sides times the side length of 11.6. And now we can just think, if I take s and divide it by 2, really that means the entire equation would be divided by 2. So if my side length is reduced to half, our answer is that the perimeter would also be reduced by half. And let's also try to solve some more questions for area given some different pieces. A honeycomb, if I start with a regular hexagon, is going to have a side length of each side is going to be 3 millimeters. So I should just be able to use those pieces to get my area. Using that same area formula, it's going to be, again, 1/2 apothem times perimeter. A lot of times the perimeter is actually easier to get first. If I know the side length is 3, and I know a hexagon has 6 sides, then we can do 3 times 6 and get 18 for a perimeter. In order to get the apothem, we have to remember back to our previous section with our special right triangles. If I know, first of all, that a hexagon has 6 sides, first thing we got to do is figure out what angle is going to go in the middle once I make that triangle for the apothem. Again, the apothem is going to go from the center perpendicular to a side, but we got to figure out how I got that 30 there. So I found that, again, if I take 360 and divide it by 6, we know that each central angle will be 60, and kind of like what we did on that last page, if I cut that central angle in half, that means that this upper angle of the triangle would be a 30. And now that I know I have a 30, 60, 90 right triangle, if I use half of that side length, the side length is 3, so if I cut that into 2 pieces, each part of that would be 1.5. So if that's the shorter leg of this right triangle, then to get the longer leg, remember if it's 30, 60, 90, I can take that short leg and multiply times rad 3. And that long leg of the right triangle is what we're looking for an apothem. So if I use that length of the apothem, 1.5 rad 3, now I'm just substituting. 1/2 apothem times perimeter will be 1/2 of 1.5 rad 3 times 18 for the perimeter. That should all give us 13.5 rad 3 in terms of square millimeters. So let's try the same steps on this next one. Again, it's still 1/2 apothem times perimeter, and just like with that last one, perimeter is easier to find first. If we know the side length is 16 and we know there are 6 sides, 16 times 6 would give us 96 for a perimeter. And we're going to walk through the same steps since we're still doing a hexagon. Should be pretty similar to find that apothem. So remember, if I take 360 and divide it by 6, each central angle would be 60 in terms of degrees, but if I'm looking at just this triangle that we're using for the apothem, I got to take that central angle and cut it into 2. So that would be 30 degrees at the top of that triangle. And just like last time, if I take my side length and I've cut that side in half, half of that length would be 8. And now if I know the short leg is 8, just like with before, I got to multiply times rad 3 if I want the longer leg, which is your apothem. And if I know that's my apothem, 8 rad 3, again, now I'm just substituting. 1/2 apothem times perimeter, that one should give me 384 rad 3. So we're going to try a bit more with figures that aren't always hexagons. So this time, if I have a square, that's actually a little bit easier. If I know a square has an apothem of 4, easiest way to solve that one is just by remembering for your apothem of a square, that's just halfway across your square. And that tells us that the side length of the square would be twice as big. So that would be 8 for a side length. And then you could still use 1/2 apothem times perimeter, but if I just want to go back and use my area formula for any parallelogram, base times height for a square is just 8 times 8, and that gives you 64 square inches for that area. And last question, if we are looking for the area of an equilateral triangle with a radius of 6, same thing, you could still use apothem times perimeter. And if I know that the radius is 6, again, a radius goes from a center of your figure out to a vertex. So from the center to the corner, that distance was 6. And a little bit trickier here with the triangle that we made. Last time for your hexagon, the angle in the middle was 30 degrees. This time the angle at the top was 60 degrees because I have to remember back to my central angles. If I take 360 and divide it into 3 sides, that means that each central angle will be 120 degrees. But just like the last one, I cut that central angle in half, and that means the angle at the top of that triangle will be 60 degrees. So if I take my hypotenuse, still using our 60, 30, 90 rules, the hypotenuse divided by 2 gives you the short side, which is my apothem. So that tells me that my apothem length is 3. And also if I want to get the side length for that bottom side, remember I take the short leg and multiply it times rad 3. So that would be half of my side of the triangle. If I remember I split that into 2, that just means the other half would be 3 rad 3 also. So if I'm looking for a perimeter, that's going to be 6 rad 3 for a side length if I add those together, and I have 3 sides, so the whole perimeter will be 18 rad 3. And now just substituting in our formula, 1/2 apothem times perimeter should give me 27 rad 3 for that. And I'm going to leave those last few lesson check answers not shown. Let's see if we can check those in class. Try those a little bit, but also we have that workbook. So trying both of those, you can get a good idea of what we need to work on in class. Make sure you have that completed for tomorrow.